So I think we've let most of the parking and traffic crowd in. As we know, we're competing downstairs against the state of the university, and I am not one to try to compete against a speaking audience with Gordon Gee. So I appreciate that you're here, and this is, if you're not familiar with this particular forum, it's in support of what was a major university initiative in natural gas utilization that we launched what is about 4 or 5 years ago now. Looking forward into the marketplace, we thought at the university that it would be very beneficial to have research efforts specifically on pulling on the demand side of natural gas in the midst of the shale gas revolution in the region. And we see that need manifest itself with the prices of natural gas and natural gas liquids being severely depressed in the Appalachian Basin. And so we are now right in the midst of a lot of efforts on campus and in the region, and as you'll see today, in partnerships with University of Pittsburgh and NETL and Gas Technology Institute, and a really exciting project that I know Getz will discuss, as well as a tri-state partnership that was signed by the 3 governors of West Virginia, Pennsylvania, Ohio, that is receiving a lot of attention nationally in the Beltway in DC and in the region to try to come up with the right pathway for economic development and research topics in this region. And so you'll see a lot of the focus is on that. To give you an update, very brief update on a few of the projects that are going on. Tim Carr, if you raise Tim raised his hand, you catch him. Catch Tim during the networking session over some wine, and about the MSEAL project, which has gone on very successfully. A lot of data analysis now, a year and a few months out of completion and stimulation. We're in the production phase, and some new results are coming out from the MSEAL project, and looking forward to where that may go. We are also working in partnership with Ohio State on the Utica Shale Energy and Environment Laboratory, which is seeing some progress over the last few months that hadn't been seen over some time, and so there's a good story to be had there on the upstream piece of the puzzle. Tim is also leading the INFUSE, the International Forum on Unconventional Gas Sustainability and the Environment, and I don't need notes for that now after I said it enough. Where we bring in at WVU through the Department of State people from around the world to teach them how we do development of shale gas in this region, and have hosted thus far Mexico, Colombia, Lithuania, South Africa, and Colombia, unless I repeated myself. And so that's a really exciting project also on the upstream side. Moving downstream, again, I'll mention, you'll hear about it from Professor Getz-Vesser, the AICHE-led newest Department of Energy National Network of Manufacturing Institute called RAPID, and we've partnered with the University of Pittsburgh, Gas Technology Institute, and NETL on that project. And our center is specifically focused on natural gas utilization. Another big effort underway, Mike Hahn, director of the West Virginia Geologic and Economic Survey here. The Geologic and Economic Surveys of West Virginia, Pennsylvania, and Ohio are working in collaboration with Doug Patchen out of the NRCCE on a project called the Appalachian Storage Hub. And in this room a week ago, it was a week ago yesterday, I guess, we had our 6-month meeting on the Appalachian Storage Hub project, where the 3 surveys are examining the geologic potential across the 3 states to store natural gas liquids, ethane, propane, butane, Y-grade natural gas liquids. And the reason this is important is because if we want to develop the downstream petrochemicals industry in this region, in particular multiple ethane crackers to support polyethylene and polypropylene dehydrogenation and all the downstream industries, we need infrastructure in this region to support that. And so the geologic surveys in this Appalachian Storage Hub project are playing a key role with lots of national attention. As a matter of fact, just yesterday, IHS and the Pennsylvania Development Office out of Harrisburg released a study on the potential of natural gas liquids usage in the region. And there, the IHS results indicate that this region with the offtake capacity that's planned and being built, could still support 5 ethane crackers the size of Shell's. Shell's ethane cracker is 1.6 million tons a year of polyethylene from 105,000 barrels a day of natural gas liquids. Do the math, and we're talking over 500,000 barrels a day, 500,000 barrels a day of ethane being projected to be used. Couple that with the offtake capacity, and we are looking at over 1 million barrels a day of natural gas liquids being produced in the Marcellus and Utica regions by 2020 or by 2022. And so all of this is coming together where we have a lot of research around the university and the region in trying to both navigate what the infrastructure build out will be as well as what technologies will come down the pipe. If we have an opportunity to build 5 world-scale ethane crackers in the region and the associated petrochemical industries that surround that, now's the time to implement the best, newest, and greatest technologies on those chemical manufacturing facilities. One of the technologies is through process intensification and modular technologies, and another is through smart manufacturing techniques, and we are also part of Smart Manufacturing Leadership Coalition led NNMI that was awarded last year called SESME, specifically focused on smart manufacturing. And so we're working right at the interface of implementing smart manufacturing data-driven analysis and real-time optimization coupled with process intensification and modular technologies. What I just described is what we think the chemical plant of the future will look like. And it looks like we're trying to build a major set of these chemical facilities in our region. So it's all exciting. And then couple that with what President Gee is talking about downstairs is proposed budget cuts due to the deficit that the state of West Virginia is facing right now on the order of $500 million a year of state budget deficit, of which there's a proposal for the university to absorb yet another $30 million of that budget deficit. So it is inherent upon us to help industry move into the state and region and stimulate our economy, so that not only we provide jobs, but economic development for the region. So that's my spiel, and I'm excited that you're all here today to hear a little bit about a few of our work going on. John Hu will be taking over to moderate the session today. We are joined by, I mentioned, Professor Gus Vesser and also Professor Josh Furchet. Josh is the Associate Dean for Research at the Law School at WVU, as well as one of the Shell Gas Mountain of Excellence hires. He is our resident policy expert. He came to us from North Dakota, where he lived through the Bakken boom, and he got here before the bust. And so now he was here for our bust, and we hope that we can see the boom again. Josh has been doing very well in the law school and is a real leader around campus on a lot of energy policy issues, and it's great to have him here. Professor Gus Vesser of the University of Pittsburgh, Department of Chemical Engineering. I think that's right. I know John will do a more formal introduction, but Professor Vesser has been a partner with WVU on a number of projects, including AICG Rapid, as well as our True Alliance, which is the Tri-State University Energy Alliance between WVU Pitt, Carnegie Mellon, and Case Western Reserve. And so it's great to have Professor Vesser on campus today. So I'll hand it over to John to do more formal introductions. I guess I should introduce John Hu, the Statler Chair of Natural Gas Utilization in the Statler College of Engineering and Mineral Resources, also a chemical engineering professor, and the director of our center. Now I'm forgetting the name of it. It's our Natural Gas Utilization Center, and I'll let John explain a little bit about that. But John, I'll pass it over to you.
Good afternoon, everyone. I think I'm very excited to see the people every year come to this is the Shale Gas Forum. And thanks to Brian to give an overview about the activities and the research in the energy field within the WVU. So today, as I think Trina and Brian asked me to be the moderator, so I'm very honored to introduce our first speaker, Dr. Weiser. Dr. Weiser currently is Associate Director for the Center for Energy at the University of Pittsburgh, and he received a PhD in physical chemistry in 1993. And I have a list of his research interests, and I'm not going to read everyone. And by the training, he is a catalysis and the reaction engineering in training. His research area covers the catalysis, CO2, chemical looping, and nanomaterials, and almost everything. He has a widespread research interest. So just the behind-the-scenes story, I know Dr. Weiser since 10 years ago. Actually, I did my postdoc at the University of Pittsburgh, and my supervisor is Irving Wender, who is also chemical engineering. So then, through the Dr. Wender, I know the Dr. Weiser. So, and then currently, Dr. Weiser and I, we are collaborating in this is the AICG, the NNMI called RAPID, which is associated with natural gas utilization. So he and I, we both actually promoting the regional activity in shale gas or natural gas conversion. So Dr. Weiser received a lot of the awards. I'm not going to name everything, but I want to highlight he received the Career Award from the National Science Foundation. As everyone knows, Career Award is a prestigious award from National Science Foundation, and he is the faculty fellow from NETL, and also here's the most interesting award he received from Catalysis Review in 2011 and 2012, and he's highlighted as a mover and shaker for the Catalysis Review. So let's welcome Dr. Weiser to give us a presentation. Thank you.
Thank you, John, for the nice introduction. I'm delighted to be here, and I was told to keep my inner geek under control and not get too technical, so I'll try to give sort of more higher-level introduction to the already several times mentioned RAPID Institute and the idea of process intensification, specifically intensifying natural gas utilization here. And I thought I'd start with a little geography quiz. Probably many of you in this audience here have seen this before, but I still find it kind of interesting to play through. This is the U.S. at night, and if you look at that, you may see or recognize a couple of familiar places. I don't know if I can get here. Obviously, on the East Coast, major cities, New York City. You have, where are we here? Chicago down here. You have Minneapolis up here. Of course, shouldn't forget Pittsburgh somewhere in there. We at least also make a little dot in the landscape. And then the big question is, what is that? This mega city somewhere up there? And yes, please. Well, in this audience, probably everybody recognizes that's the Bakken, right? I mean, this is these flares burning through the night up there. And we can go to the south, and again, we see the cities here, San Antonio, Austin, Dallas, Houston, and then again, this strange formation that is down here, which again is the Eagle Ford Shale. And you can go on and on with these things. And when you look at the numbers here, when I first heard the numbers and went over, then actually I had some emails going back and forth with John because I just couldn't quite believe, and I thought I made a mistake somewhere. There are about 3,000 flares. They're burning about $100 million worth of natural gas every month. I mean, it's absolutely staggering. And obviously, they're not, they're bright people working there. So why do they do this? And the simple reason is it's remote, right? It costs about, the latest price tag that I could find was from 2014, about $9 million a mile to build a land pipeline. So that basically means for these $100 million a month, you get basically 10 miles, 11 miles of pipeline out of that. So for a year, you get about 100 miles of pipeline. So if you really build the pipeline network you need there, it takes you years to recoup this cost. And unfortunately, it's not just the U.S., right? This is worldwide. This is, again, the world at night with just the flares worldwide indicated, the Arab Peninsula, the Maghreb, Russia, Nigeria, Venezuela, and of course the US as major emitters. And we have the questionable distinction here in the US to be ranked number 4 in the world for our flaring, and the even more questionable distinction of being one of the very, very, very few countries where flaring has significantly increased in recent years. Again, why is this? Oh, just again, the numbers, $15 billion per year that are being flared off, resulting also in CO2 emissions, aside from the financial loss here, CO2 emissions that correspond to about 80 million cars, or about 130, according to my estimate, 130 medium-sized coal power plants. It's really staggering. And the reasons are pretty simple, of course. I mean, associated gas is a low-value byproduct of oil production, basically, in most cases. The small and varying volume of the associated gas isn't well matched to the existing technology that we have to convert this gas in any way. And again, mostly these occurrences are in remote locations. And even when they are like here in the Marcellus, we see we don't have the infrastructure in place often to really take care of this. I was surprised to see also a lot of flares that the Marcellus shows up nicely at night, if you want to call that nicely. In these pictures here. So we don't have the infrastructure in place, and we are often lacking, again, the regional markets to use this. So we're dealing with stranded gas, basically. And then you have two options. Again, you flare it, or you turn it into something that is more easily transportable. And it seems like a no-brainer, right? A gas to liquids, you have a higher value product, it's easily transportable, it can be blended in even with the oil that you're getting. So an easy solution in principle. Why don't people do it? Very simply because our current technology doesn't scale, right? Our whole industry, our whole technology has moved to a point where we are absolutely following the paradigm of economies of scale, right? I mean, everybody has probably learned the 6/10 rule or 2/3 rule, where the price increases with about 6/10, or the volume to the 6/10 power or 2/3 power. And that means basically we are building larger and larger units here, going to these mega units like the Shell Pearl plant that is shown here. But there's starting to be some doubts about the whole thing. You can already see here with Escavos and Pearl, we're starting to deviate from this nice line that we otherwise have seen. And people are wondering whether the complexity of these mega plants has gotten to a point where basically economics just doesn't keep up with things anymore. There has been a famous, often cited studies from the Rand Corporation in the 1980s, where they studied a whole range of mega projects around the world, from somewhere between $500 million to $5 billion at that point. And they found that the average cost overrun for these plants was 88%. If you take here, Escavos was originally estimated to be between $1 and $1.2 billion. It ended up being more than $5 billion. The Pearl plant was originally meant to be about $12 to $14 billion. Then in the end, they claimed the price tag was 24. What I hear through the grapevine, it was actually over $30 billion. So the cost runs away so massively that basically ultimately your economies of scale doesn't hold up anymore with that. So the question is now, can we break out from this? And in particular with these remote locations, these small resources of natural gas, comparatively small resources of natural gas that we want to use, can we go down to a small scale again? I mean, this is obviously not a huge scale, a jump indicated here. And can we do something to bring down the cost on these small scale units and break away from that? And the idea behind it is exactly what is captured in this process intensification. It's a trend that has been going on for quite a while in Europe, and frankly, the US is a little bit late to the game here, but finally waking up to this. This came out of a long series of workshops, some of which I was involved still when I was back in Germany. A definition that was really fought over for a long time, and you could hold a whole presentation just on that topic here. And they ended up with this definition here: a set of often radically innovative principles, a paradigm shift in process and equipment design, which can bring significant, more than a factor of 2, and there were endless discussions over that number, benefits in terms of process and chain efficiency, capital and operating expenses, quality, waste, process safety, etc. So that basically is the big picture. What is process intensification? It's basically doing more with less, in a sense. Again, the U.S. was quite behind the development here for a while, and I really want to give a lot of credit and a big shout out to the person who really has brought this to the forefront here in the U.S. Dan Boyson, at that time at ARPA-E, was discovering basically this gap in the US and was pushing hard and finally managed to get actually process intensification on the US Senate Energy and Water Appropriations Bill in 2016, where it says explicitly it's the Clean Energy Manufacturing Institutes are encouraged to consider a modular chemical processing as a way to address the issue of natural gas flaring. So it was built, the whole initiative was really built on the whole issue of flaring. And out of this finally came then the call for proposals last summer, where again, John Hu and I worked closely together with a large team led by ASCHE to compete for this, and were ultimately successful in being awarded this 10th Clean Energy Manufacturing Innovation Institute, Rapid Advancement in Process Intensification Deployment Manufacturing Institute. That always has to be on there. Again, it's led by ASCHE. It's a very large consortium. The numbers are changing almost by the day, but right now, when I put this together last week, I think we are about 71 industrial partners, 37 academic institutions, 9 national labs, and 6 NGOs. And it's a fairly broad institute. You can see here it is in its current configuration, has 6 focus areas, basically broken down by 3 application-driven areas: chemical commodity processing, natural gas upgrading, and renewable bioproducts. And then also 3 fundamental or enabling technology: intensified process fundamentals, modeling and simulation, and module manufacturing. They obviously support sort of the other activities there. And again, the natural gas upgrading is the one that is directly relevant for us here, of course. The University of Pittsburgh, we are the leads here with a co-lead of University of Michigan. And again, our key partners here are and have been through the entire proposal stage, West Virginia, NETL, and GDI. Let me go back to sort of make it a little bit more concrete. What are we doing? What does it mean, process intensification, when you apply it to natural gas? Again, we have natural gas, methane, the main component here. I'll focus on that. And in principle, you have 2 ways how to convert natural gas into liquids. You can do it in a direct conversion pathway or an indirect conversion pathway. Where the direct conversion pathway basically has 3 main options. You can either, in a direct step, convert methane without an additional reaction partner, convert it to aromatics, typically so-called dehydroaromatization. You can oxidatively couple it, so you add some oxygen in, but you basically do an oxidative dehydrogenation combined with a carbon-carbon coupling to get the C2 product out of that. So you form ethylene, ethane and ethylene, but ultimately you want to go to ethylene. Or you can do really the holy grail, the selective partial oxidation, directly insert an oxygen molecule into a carbon-hydrogen bond and go to methanol or formaldehyde, but methanol obviously would be the target you would go for. That's all great and good, but unfortunately, it doesn't work. At this point, the technology isn't at a stage yet where we can make it industrially work. They're all hampered by very low yields that simply are economically not quite feasible yet. The problem is simply that methane is an extremely stable molecule, right? The first hydrogen abstraction, almost 440 kilojoules per mole. You have very low yields. You have thermodynamic limitations on there, kinetic problems. You have coke formation. We don't really have good catalysts to do this. I mean, it's basically, it's all of chemical engineering rolled into one big problem here, right? So we are all hacking away on this, and I'm optimistic that we are not too far away from making some of these routes work. In fact, there is now a company, Siluria, that is strongly pushing an industrial scale process for oxidative coupling. Daring, in my opinion, but they're going for it. Good for them. So we'll see it. The other one is the industrial reality. Indirect conversion of methane to liquids is in industrial realities. You have basically 3 different routes how you can turn methane into syngas as an intermediary step, either by steam reforming, autothermal reforming, or partial oxidation. And then from syngas you go again to whatever you want, methanol, olefins, gasoline, or any of these steps. Works, but again, has also its challenges associated with it. It's a very complex multi-step process by its very nature. It's not very energy efficient, in particular the steam reforming, which is by far the dominant route that we have in industry, highly endothermal process, large energy consumer. You have some issues with coke formation. Catalyst cost is a major issue when you go to partial oxidation, which would be energetically much more favorable. And again, you need a cheap oxidant. The oxidant is a major issue here. That's basically the whole reason why we have steam reforming, because water is actually a very, very cheap oxidant that you can use. So again, that's the state of the art, steam reforming of methane. You take methane and steam, you turn it into syngas. It's a multi-stage process here. You can see there's a lot of steam going around here. Actually, the engineer at Lurgi, who years ago gave me this little schematic, told me it's basically a big steam engine that also happens to make some syngas on the side. I mean, that's really almost the way you have to think about it. Very endothermal, gives you a hydrogen to CO ratio, which is 3, which is too hydrogen rich for your downstream processes. You really want to have 2 if you go to methanol, if you go to Fischer-Tropsch, which are the main processes. Relatively slow, so you need a long residence time of about 1 second. In other words, you need large reactors, and again, very complex. Now, you have partial oxidation as an alternative, and partial oxidation from its very basis is actually a much smarter process, if you like, right? You convert directly methane with oxygen to CO and hydrogen. It's an exothermal process, so you don't need to supply heat to the process. It runs autothermally. It gives you stoichiometrically directly the 2-to-1 ratio of hydrogen to CO that you want to have, so you can do it in a single step. You don't need water gas shift, cleanup steps afterwards. You don't need a pre-reformer. You don't need all these additional unit operations. The nature of these catalytic oxidation reactions is much, much faster. They're much faster kinetics, so you can bring down residence time into the millisecond range, so you can shrink your reactors by an order of magnitude or more. And again, because you don't need any external combustion to fire the process, you basically could run a process with virtually no emissions. I mean, you don't have 100% selectivity, so there always will be some emissions, but I mean, it's nothing compared to the steam reforming process. So why don't we have this? This reaction has been around for at least 50, 60 years at this point here. The reasons are very simple. Again, you need to run this with oxygen. You can't use air, otherwise you dilute your syngas stream with all that nitrogen in the air, and you get NOx problems and all these things. So you need a very costly air separation process. You need a very expensive noble metal catalyst. There has been a lot of work at Eni and Haldor Topsoe and other companies in coming up with better, cheaper catalysts for that. Nobody has really found a really good one so far. And then ultimately, you have major safety concerns because you're operating a methane-oxygen mixture at very high temperature, pretty close to the upper flammability limit. So I remember I did my postdoc at the University of Minnesota when they had a contract with Roman Haas, actually investigating this process. They had a small pilot plant in Texas, and the student came back one day completely shocked and said, well, they have this plant here. They have built sandbags all around the reactor and do remote control because they are scared out of their wits that something could go wrong. So it's theoretically a great process. In practice, a lot of challenges. So we had been thinking about that a while and had been working on a process for combustion, which has a really interesting history, almost 100-year-long history in itself, so-called chemical looping combustion, which is one of the most promising clean combustion technologies that people are working on right now. And I won't go into any details, just very briefly walk you through it. The idea is you take a solid metal component, you contact it with air, so you oxidize the metal. Here the example is nickel. You contact with air, so it gets oxidized to nickel oxide. You take the metal oxide, you transport it into a second reactor, and now you flow pure fuel, in this case methane, over it. And what you do is basically a conventional combustion reaction forming CO2 and water, but now with a solid oxidant, the metal oxide. The metal oxide gets reduced back into the metallic form, which then gets transported back into the first reactor, closing that chemical loop. That's where that strange name comes from. Again, overall, a very conventional combustion reaction, but the advantage is that you never mix air with the fuel component, so you basically have an oxy-fuel combustion without air separation. So you can condense water out of the effluent stream here and immediately have, without further separation, a need for separation, a high concentration sequestration-ready CO2 stream. So chemical looping is basically being sold as a really efficient carbon capture technology, but when you think about it, it really is, you're kidding me. Okay, it really is a fuel processing technology with integrated air separation. So we basically took this technology, and I really have to jump here now, and applied it to partial oxidation, right? So we basically we developed new materials by combining nickel and iron to convert methane in the same process now selectively to syngas. And let me really jump over all of this here and show you just as a result, we were able at this point, we have actually by now improved, I should have updated this here, we have improved methane conversion of 90%, hydrogen selectivity of over 80% with a direct hydrogen to CO ratio of 2:1, where we don't need an air separation unit. We have no flammability concerns because we never mix methane and air, and we use 90% iron as our carrier material, so a dirt cheap material. So how is that process intensification? That's the whole point why I'm talking about this here. We reduce the spatial footprint. We have fewer process steps, no water gas shift, no air separation unit. We have fast kinetics, so much more compact units. We reduce the energy footprint. We have an exothermal partial oxidation process. Again, no air separation unit, which is a major energy consumer otherwise. We reduce the environmental footprint. We have minimized CO2 emissions. We have no combustion process here anymore. We improved process safety. Again, no pre-mixed methane oxygen mixtures. And we reduced the economic footprint, again, by having fewer units, by not having to run air separation unit, and by having really cheap carrier materials. And all of that we achieved through a combination of change in reaction pathway, which is mostly behind the white points here, and change in the process technology by doing chemical looping, as highlighted in the yellow steps. Okay? So that hopefully, and we haven't done any techno-economic analysis yet, but that hopefully will allow us to come down in this step here, but we're almost certainly not going to come down to these levels. So we need something else. And the something else needs to come in basically through advanced manufacturing. That's the hand-in-hand companion to these developments. And here is a slide again from Dane Boysen, where he usually shows this new paradigm, economies of unit number, and relates it back to the Ford Model T, where you can see a similar learning curve as we saw in the economies of scale. And this is a point where I actually disagree with him a little bit, because I don't think the Model T is a good example for this. If you look at this here, this is the Model T cost versus production. And you can see the real savings come in when they go up. They started with about 10,000 cars per year that they produce, and very quickly went up into the million stage. We will never build millions of syngas processes, right? I mean, I don't think this is really what we need to aim for. What we need to aim for is something that is more akin to the famous Moore's law. This high integration, this continued integration of more and more units, in this case, obviously, it's just a high integration of the CPU, that results then correspondingly in a steep drop in the cost. So the increased volume basically incentivizes efficiency improvements, standardization, and all these benefits that come with integration. So the economists often summarize this under the learning curve, right? So what do we need here for our natural gas development? Automation, advanced manufacturing, 3D printing, advanced controls that will allow us to bring down the cost. Labor efficiency, specialization and experience. We're only starting to really see what we can do in 3D printing for complex things like a chemical reactor. And of course, standardization, efficiency increase by standardizing the production, but also standardizing interfaces between different modules. And then ultimately points that go more to the community that we're building here. The shared experience effect, building a learning community to transfer the insights. It's no coincidence that you have Silicon Valley, where you have Google and Apple and Facebook and all these companies across the street from each other, and fertilize the whole area in that regard. And then again, economies of scope. We saw that development in Japan in the 1980s. They started out with TVs that they made, and the technology and the insights they developed there, they transferred little by little to basically all of consumer electronics, for which Japan then became absolutely dominant in the 1980s. So that is also another point which is behind this Rapid Institute, creating the community where we have the shared experience and really can work together to accelerate this development across these things. And I want to add up with my last slide here, a final caveat on this here. Of course, there is no direct analogy here between cars and computers to chemical reactors. I mean, those are the poster children of this development here. The cars and the computers created and were products with entirely novel qualities and created entirely new markets, right? I mean, nobody could have imagined when they made the SUSE Z3 that you would have basically a computer that is 1,000,000 times more powerful in our palm, and all the amazing things that you can suddenly do when this. We basically discovered this only by doing it, little by little. And there were entirely new opportunities that were developed here. The natural gas market is quite different, right? It's a very mature market, it's very competitive, so it's very difficult to get in there. And the products that we make are the same products. The syngas that we make is not a different syngas. If we make a C2 product from there, it's going to be the same C2 product. So the new point is, and that's sort of looping back to the beginning, we are utilizing a new resource, right? The opportunity for us, at least in the starting point, is again in these flared gases that are basically a free resource that comes to us with environmental benefit and huge cost advantage. And where we can take it from there, who knows? And ultimately, I want to end with this quote here that is attributed to Thomas J. Watson. There seem to be actually serious doubts whether he ever stated that, but as we learned from the White House, never let the facts get in the way of a good story. So I think there is a world market for maybe 5 computers. Obviously, he was wrong because he didn't see all the opportunities that developed once the computers were available. So maybe there is a market opportunity for small-scale decentralized gas-to-liquid or X-to-liquid units once we have them to spread far beyond that and really stimulate then also an economy where maybe Pittsburgh to Morgantown can be the next Silicon Valley for a development in this regard. So with that, thank you for your attention, and I'll pass on to Josh, I guess.
Thanks, Dr. Weiser. I think we will save the question to the end. I think Dr. Weiser gave a very good presentation, especially on how you try to commercialize the natural gas to liquid or to the high value product. Actually, I would like to the audience to remember what he said in one of the commercialization approach. If you go to the GTL route, costs you $24 billion. Actually, the brand helped me and to organize a AICG workshop in November. Some of them attended. In the AICG shale gas workshop, they actually say that the GTL plant built by Shell in Qatar cost $24 billion. You heard of $30 billion. That's probably the first one and last one in the world. There are only 10 companies, not energy companies, 10 companies in the world can build that one. So what the point I think that Dr. Weiser made is very good. So what the rapid that WVU and UPID we are in really promote the process intensification that we work on the smaller scale, drop the cost to the certain level, then have the advanced manufacturers kick in, then we beat the so-called large scale economy of scale. So I think that's a very good point that Dr. Weiser made. Okay, with that, I'm going to introduce the second speaker, and Dr. Josh Fauché, and then actually I'm pretty sure the audience know Dr. Fauché, and I know Josh from the day one I joined the WVU, and largely because I'm heading the WVU Shale Gas Center. Now the name is called the Center for Innovation in Gas Research and Utilization. And Josh and I, we actually try to realize the mission set by the WVU to realize how we utilize the shale gas from the upstream that the team is leading. So we try to utilize. So both the upstream and downstream, we work together. So Dr. Fauché is currently Associate Dean of Faculty Research and also Professor of Law, Director of Energy and Sustainable Development in Law. And his research interests are also widespread. I'm only highlight the top 3 of his research area, and in the geothermal energy, climate policy, and renewable energy. And I also want to mention that in the WVU Shale Gas Center, there are 9 faculties currently working with me, and I'm heading the leading engineering research area, but Dr. Fauché leading the policy and law, the research is really the good area that Josh is leading. And also before he joined, Josh joined WVU, he's the Associate Dean at North Dakota and in the University of North Dakota School of Law, and he published a lot of the articles and book chapters, and I'm not going to mention the one. And also, before he came into academic, and he also practiced the law and also the policy in Washington, D.C. So I would stop in here. I would like Dr. Forshade to present his research.
Thank you, John. I very much appreciate it. I have a law background. I have started at a law firm in Washington, D.C., where I did electricity and natural gas regulatory work. When I went into academics, I worked with groups trying to deal with pipeline siting and transmission line siting and electricity generation siting. Got to North Dakota in 2007, and the hot thing in North Dakota at the time was wind siting. By 2008, it was very much an oil and gas issue. And so really transitioned my work from renewables and grid integration into oil and gas. And so I've really made a transition in my research. And what we're seeing now is this is kind of coming full circle. That is the role of natural gas, particularly in the electricity sector, is really bringing those two worlds together. So with some question time, we can talk about other things. I will try not to be too much of a lawyer on some of these things, which is probably not possible. But I want to give you an idea. One of the things in my work, when we talk law and policy, particularly in the energy sector, we really have to look at beyond law and beyond regulations. We also have to look at some of the history and economic theory behind some of the things that we're doing. And the economics of natural gas is driving the market, and how we look at it needs to evolve. That is, from a regulatory and legal perspective, we need to evolve with the market that's before us. And so one of the things I want to talk about is a little bit of how that has changed. And there's three basic things that we've learned, and I think that this is something that I couldn't say 10 or 12 years ago. That is that natural gas is here to stay. I don't think anybody thought it was going away, but it seemed to be really kind of a depleting resource. At least that was certainly how we treated it from a law and policy perspective. We're seeing natural gas as the predominant choice for electricity generation, and we're seeing that it's certainly something that impacts West Virginia directly, but all over the country. And we see opportunities of it as a firming resource. That is something that can support renewable generation. And lastly, natural gas, and there's research that suggests natural gas should be the direct transportation sector fuel source, including some of my colleagues who are doing really interesting work on that front. But one of the things that I'm seeing is that maybe that's not what it should be, that it should be something that supports the transportation sector, and I'll talk about that in a second and how that fits. One of the things that we're seeing, and this impacts how we view law and policy in this sector, in 2007, the average price for natural gas per 1,000 cubic feet was $6.25. 2008, it hit its peak at $7.97, with the expectation that that was probably going to start moving up. Well, hydraulic fracturing and horizontal drilling changed that significantly, and you see the prices between 2007 and 2012 dropping down to $2.66. The beginning of the year, we were back around $3 and $3.25, and just yesterday, the spot price anyway was $2.93. Low prices change what's possible in the energy sector. This is true for electricity generation. This is certainly true in manufacturing and other opportunities that didn't really seem feasible 10 years ago. So as an example, the electricity generation sector, if you look at 2006, we were at almost 49% of electricity generation came from coal, with 20% coming from natural gas because natural gas was expensive. You see, by 2008, we start to see a shift, and by 2015, coal and natural gas are around at parity, both around 33% of generation. That's a huge change. The change from a drop in 15% in coal consumption for electricity generation is a major issue, obviously, for coal producers and for those utilities. An increase in natural gas facilities by 12% in that time frame is significant, and we also see a major increase in renewables. Some of this is from production tax credits, investment tax credits, and other subsidies that are put in the renewables market. But the greatest increase that we're seeing in 2012 to 2015, where we really see that start to jump, part of that is the projects coming online, and part of that is that renewables play well with natural gas. And so this is something we can expect to continue to see. Back in 2007, we were looking at renewable portfolio standards around the country. Those are requirements of a certain percentage of electricity coming from renewable generation. There's 29 states that already have a renewable portfolio standard. There were proposals at the federal level. And looking at those numbers from 2005 to 2030 was our anticipation. One of the test cases that the Energy Information Administration looked at said, well, we think we're going to see roughly an increase in 1% of electricity costs if we had a 15% mandate for renewable electricity. Notice that we're still pretty far off from that. The whole idea behind that, though, was assuming that natural gas prices would continue to go up and that you would have renewables come online and push those down because of a lowering of demand. All of that is out the window with the glut of natural gas that we have right now, and yet we continue to see renewable energy surge. And so we'll talk about where that fits in. But part of this glut of natural gas that's lowered prices goes exactly to what Gus was talking about in places like North Dakota. When you have a commodity in a place that it doesn't do very much for you, and I can say from North Dakota, I mean, you look at those lights, there's not that many lights that you could turn on in the state of North Dakota to support even a blip of that. There's 700,000 people in the state of North Dakota, right? A state that's about 3.5 times the size of West Virginia. 700,000 people, all sorts of electricity opportunities. They have wind coming online. They have the Garrison Dam for hydropower, lignite coal, which doesn't ship well, so you're burning it where it is. Overcapacity of electricity, so there's really no use for this natural gas on site and where it is. And so it really does become, how are you going to move it, or can you build something with it? And even that becomes a challenge when you have population centers, 700,000 people. You don't have the people to populate a manufacturing plant or to fill them out. The population there is relatively well educated, but you just don't have the numbers. And the examples we saw even during the oil boom of people coming in from all over the place in North Dakota. Menards, which is a big box store like Lowe's or Home Depot, built a store in Williston, North Dakota, for example, and they would fly people from Wisconsin on the company jet. They'd work a week, fly out for a week, and fly back for a week because they couldn't find people who could staff the stores. Towns of 7,000 went to 10 and 12,000 people in less than a year and a half. And so you have major infrastructure problems and major challenges, which explains in part why this commodity that we spend millions and approaching billions on to develop in other regions is being burned and being wasted there. And so population and access to use it matters too. And we have to figure out that part of it. And that's an advantage that this region can have. We do have population center and access to population here that other parts of the country don't. And so the natural gas really can be a useful resource here in ways that perhaps it can't be in more remote regions. Despite the decline in prices, we saw a significant increase and continuing increase in natural gas production. Some of this is because as this process has developed since 2008, it's cheaper and cheaper to drill longer and longer. It's more efficient. We're getting more more gas from less wells. And so despite the prices, we see this continue. And we also have a legal infrastructure here that influences that. That is that we had a number of people during the boom, everybody goes out and signs leases so that they can go out and drill. But the traditional lease runs between 3 and 5 years, and if you haven't drilled and started producing, that lease goes away. And so you have your sunk costs in that process. And so you have incentives to continue to drill, hoping that the price is going to go back up. But of course, if everybody's continuing to drill, hoping the price is going to go back up, and as we see this production go up, the price doesn't go up with supply unless you find a way to use it. Now, interestingly, this is a chart, and I don't know if you can see it that well, but the top chart is electricity generation, which has been relatively stable. With the use of batteries, demand for electricity is going up a little bit, but has been relatively stable over the last 8 to 10 years. What we do see is a shift to some degree in the resource. And again, that's where we started. You see the red line there at the bottom is hydroelectric, which is very stable. We haven't built a whole lot more. It tends to be pretty intrusive and pretty expensive. Once it's built, of course, you don't have a resource cost. Right? That's the beauty of hydro. Once it's built, it runs. The same is true for nuclear, and you see that similarly there. That's the yellow line. Again, very stable. Nuclear has been about 20% of our electricity generation mix and continues to be there. The green line, though, is natural gas, and the orange line is coal, and you see that those cross sometime around 2015 where they're about even, and you're seeing natural gas increase. And the reality for that is the economics of producing electricity from natural gas. And even locally in this area, 2 years ago, major electricity utilities were telling us that coal was still more efficient and still better for them, and they have changed that now. Now with the price and maintaining price of natural gas and the drop in wind and solar that they can now integrate because they have more gas online, the prices are really becoming more economic for them to continue their fuel switching. And that is a reality that is being driven primarily, if not exclusively, by the price of natural gas. Interestingly, though, as we look at these low prices and the increase of natural gas coming online, electricity prices are not dropping. So that is the input and what we use to develop electricity is the inputs are dropping, but you have high costs of switching to new facilities, switching to natural gas. And so at least for now, prices are staying relatively stable. So consumers are not seeing the benefit of this change, whereas manufacturers and others who use natural gas as an input can see that as a benefit. But what we have seen is a reduction in emissions. The other thing, when we talk about climate policy, in the United States does not have a comprehensive climate policy, even though they do around the world. Almost exclusively, at least in the electricity generation sector, almost exclusively reductions in emissions have come from the use of natural gas. From 2007 to 2012, we saw a reduction of 12% in the electricity sector without any carbon regulation whatsoever at the federal level. That beat Europe and other areas of the world that have carbon reduction mechanisms. And that is almost exclusively, if not exclusively, because of the use of natural gas. And so you have this clean product, relative to other opportunities, that is actually having an impact on climate policy without anything other than economic support. So what does that mean for law and policy and how we look at this? Well, the main thing is gas and wind and solar work well together. The real challenge that we see in coal and nuclear, by the way, nuclear plants are built. The cost of fuel right now for a nuclear plant is relatively negligible. Right? It's just in operations once you've got the plant built. And they're still struggling to compete with natural gas plants. That is in part because there's no adder or benefit to them to run as a carbon neutral or emissions-free electricity generation source, but it's also because coal and nuclear are not fluid products. That is, coal plants and nuclear plants are either on or off. You run them at about 80% efficient, or at least about 80% to be economic. And it's not to say there isn't a role for coal or nuclear. Both are baseload power and as built, tend to be very strong and useful sources, and it's why coal is still the dominant source around the world. But unfortunately, around the United States, 80% of the coal being burnt in coal plants is in plants that are 30 years or older. And that is problematic for the long term. And so because wind and solar are intermittent resources, that is, the wind is not always blowing, the sun is not always on, it works well with a product that can turn on and off, and natural gas is that product. Just like we see at your stove at home. You turn it on and you turn it off. That's why we don't use, well, as much as I might like a wood-fired pizza, it's not very efficient for cooking the kids' mac and cheese, right? We switch to natural gas as the one that works well with intermittent needs. On the transportation side, one of the challenges of switching, and I've been doing some research on hydrogen policy, switching to hydrogen vehicles, switching to natural gas vehicles, and looking at what that process is. And we have seen for years, right, when the first automobiles came out, we had both electric vehicles and gasoline vehicles, and gasoline became the standard. We don't tend to fuel switch easily. And so the idea that we would switch, for example, from for our primary transportation sources, from gasoline to natural gas or hydrogen, and then eventually maybe to electricity, it doesn't make a lot of sense to go through that process. And companies like Tesla and the Chevy Bolt and some of the other cars that are coming online with their increased ability and range suggest that electricity might be the way to go because natural gas can develop electricity and you don't have to fuel switch, right? These lights are almost predominantly turned on by coal, but if we evolve to use it from wind or solar or natural gas or nuclear power, these lights still turn on. And the same is true for other vehicles using those sources. And so one of the challenges is figuring out where do we use this resource. And I guess where I'll try to wrap up here is to say where I started. Regulators need to evolve like the companies in the sector. The companies are responding to economic signals. They are shifting to the supply of natural gas that's available and the cost of getting that into their generating facilities and bringing electricity to market. And the markets are actually working. Nothing has been more efficient than evolving the electricity sector than inexpensive natural gas. But it's not the market outcome that most economists and most of us expected 10 years ago. Technology can change very rapidly and certainly has in this sector. And lastly, building for the future, and this is one of the most important things that we look at when we talk about what we can do for natural gas utilization, is building things. Right? We have had a history in this state of taking our natural resources and shipping them elsewhere where people use it to build things somewhere else. And the opportunity here through things like the cracker plants and other manufacturing opportunities, if we're going to move things forward and start developing this area, we need to be building things with our resources. And that's the real opportunity that we see here. And as long as we have a foreseeable low price of natural gas, I think that's an opportunity that needs to be pursued. So with that, I think I'll wind up, and thanks very much for your time.
Thanks, Josh. I think Josh gave a very good presentation from the different perspective, from the regulatory and market side, and then the key is, we have a low cost of the natural gas, and then do something basically. So for those who do not know currently the regional price, I can give to you because I saw one presentation slide Brian gave to me. If you look at the nationwide, true, the natural gas, the price on the million BTU basis is probably $2 or somewhere around the $2 to $2.50. However, in this region, actually it's less than $1. And also the more interestingly, for those who do not know the natural gas, there's a component in the natural gas called ethane. It's not just methane. The price is like almost 4 or 5 cents per liquid gallon. It's basically cheaper than water. So the point I think that we try to make here is that do something and upgrade the value of the low cost natural gas and to something valuable, either from the utility transportation sector or from the chemical sector, like Dr. Weiser said. So with that, I think I would like to open the questions, and any question to these two speakers, please go ahead and ask. Thanks. Yeah. Go ahead, Dick. Always the one.
Okay, thank you, Trina. This question is for Götz. As we look at electricity, we talk about distributed generation, having the generation right where we're going to be using it in our neighborhood. What kind of size plant would you see process intensification making so that we might talk about a distributed generation for the, say, the plastics industry? And what kind of infrastructure would you need to make that happen?
Yeah, that's a very good point, and obviously I didn't talk about that at all. I mean, once we make the gas liquids, the next question is, what do we do with this, right? I mean, we have two alternatives. One alternative is simply you make gasoline, you mix it in with the oil that you make in the back and field and transport it away from there. Probably a smarter solution would be to turn it further into higher value products right on location and build the regional economy on that. You will run into the same issue that I discussed here for the gas to liquids there. I mean, how are you going to be competitive with a much smaller scale polyethylene plant, for example, or whatever it might be, compared to the large scale plants like the one that Shell is planning in Pittsburgh now? Again, the answer must be in smarter technology, higher integration, higher automation, and again, the same kind of modularization that we aim to apply for the gas to liquids. And that is, again, where I meant this kind of shared experience effect, the learning curve comes in. Hopefully, as we learn how to do this in efficient ways with this really kind of vastly available and cheap resource, natural gas, we can apply the lessons we learn there to the downstream technologies. But again, there is no immediate answer to that. Right now, if we make OCM, oxidative coupling, work on small scale and we go to the C2 product, we will still be stuck at the point that turning the C2 into the polyethylene is going to be too expensive to compete with the large polyethylene. To some degree, maybe again, it's also a call to politics to come in and create the regional policies that encourage and at least in the initial stages, subsidize this development, so you can actually build these first plants there, maybe at a higher price point, but still with subsidies be competitive, so they can develop that knowledge and know how to bring down the price and really become competitive.
I'm just curious, the inventions that you see will need to be made in order to be able to do this modular manufacturing, taking gas to liquids here in this area and make it profitable. How long is that going to take? And is the natural gas resources from the Marcellus Shale going to be available at that time?
I mean, interestingly enough, many of these technologies exist, right? I mean, when I talked about the process intensification, many of the technologies, the prime examples for intensified technologies, take the chemical looping. It was invented about 120 years ago. It has been around forever, but it hasn't been demonstrated at scale. It's a new technology. Back then, there was no incentive to really develop it further. We have the incentives now. It's a technology that has been developed or demonstrated in many small-scale labs, but again, I just had a discussion with my students in class about that. Why is Shell building the good old steam cracker when you could have oxidative dehydrogenation or things like that? If you spend $6 billion on a plant, your risk tolerance is 0. You are not risking anything. And as long as nobody has demonstrated oxidative dehydrogenation or chemical looping or whatever it might be at scale, companies will be extremely reluctant to do it. So it's a catch-22 situation. Who is going to take the risk first? That's the big advantage, also the big opportunity we have in going to small-scale units. Now you're talking about investing maybe $100 million rather than $6 billion. Now the risk tolerance is entirely different. You can dare to be a little bit risky and try something which looks like it ought to work because it worked on a really small scale. And you learn as you do it.
John, one thing I would add to that, I completely agree. And one of the challenges that we've seen historically with energy subsidies, the Energy Policy Act of 2005, the Bush administration supported in Congress sent a bill with an 80% loan guarantee for nuclear plants. It led to no construction of nuclear plants based on that loan guarantee. That's a good loan guarantee, right? 80% risk, but it's so much money that these large-scale projects also have an opportunity cost problem. That is, if I've got $20 billion to put into something, am I going to put it into one project, or can I diversify it into a variety of different ones? And that's what the small-scale projects can also do, and I think it's actually what we're seeing to some degree with natural gas fired utility, natural gas utility generation. You can build a smaller scale one in a smaller place, and so your risk profile is lower, and you can diversify your portfolio in a way that's safer, and you can be more innovative and take some chances in a way that when you sink $6 billion into a plant, you're not nimble. And I think that's one of the other big problems that we're seeing on all of these energy projects.
So this is kind of a regulatory question. When I listen and speak to people who are experts within the energy field, there seems to be a fairly common consensus that the price of natural gas is the death of coal, right, or was the death of coal. The political and public narrative appears to be that it's regulations, and if we just undid the regulations, there would be a miraculous, I don't know, coal would drop below the price of gas. So can you speak to what appear to be two, sort of the experts are saying one thing and the narrative seems to be saying another?
Sure. I think one of my colleagues said, to the extent that there was the Obama administration had a war on coal, it was largely ineffective. So there's a question about goals versus effect, right? And so there may have been an interest in significantly reducing coal over the last 15 or 20 years from a variety of sources. It was not effective until we had cheap natural gas. And so those of us who have looked at the industry are looking at the impact. Cheap natural gas, you can track it. I showed you the numbers. You can watch the change. Coal moved because of that. Now, part of this is the narrative that I was talking about before. If you go back to 2007, reducing some of the regulations on coal would have made it even more stable and even more profitable. Because there were, when you add scrubbers to some of the plants and you add some other things that you need to do to reduce emissions, there's no question that there was some added cost there. Natural gas prices at where they are now and where they have been since 2012 anyway, is such that it doesn't matter. You've blown the cost of scrubbers out of the water. And so the narrative where it started probably had some truth to it, but the more current reality and the more recent reality is natural gas prices. And so I think to some degree both sides are speaking, there's some truth on both sides of that analysis. But I think the natural gas prices right now are the reality. And I don't think that there's any regulation, absent some heavy subsidy, that actually said we're going to give this to coal to try and reduce its price so that it's on par with natural gas. But that cost, I don't see where that money would come from. We certainly can't do it in this state because I think we would have tried it. We just can't get to that number because the cost of gas, as John just said, if you're looking at it less than $1 an MCF, I don't see what can compete with that. And so that's just an economic reality, I think, at this point, that it's natural gas now anyway.
Yeah, I totally agree. I think basically what you're talking about is maybe a little bit of shift at what point the dropping gas price would have dropped below coal. So without regulation, again, maybe coal would have been a little bit cheaper and it would happen a few months later or something like that. But effectively, it's the cheap gas.
And there's an awful lot of pipeline building going on that's going to carry a lot of this resource out of the region, up to Canada, down to Florida, even west, toward the Mississippi River. So when we're talking about the availability of the resource for these other value-added type activities, if you guys could comment on that. And then the other thing, we are at a university and we're all university professors. Is it too early to start challenging our undergraduate students to be thinking in this new paradigm of smaller is better, and even in the courses or in keystone projects or things like that, start challenging them to see if the new ideas come from there?
Well, clear answer to the second one, absolutely not. That's what I'm doing. I'm already teaching a class on process intensification. In my undergrad core class on reactor design, I have a big element in there already for a number of years teaching the undergrads. This is how you bring change in the marketplace, right? I mean, I'm a firm believer in Thomas Kuhn's theory that the paradigms change happen by the old farts dying out, basically. It's not like we suddenly rethink what we're doing. It's just the people who have learned it one way die out and the new people come in with new ideas. So yes, we absolutely need to teach our students to do it differently. So subversively, they bring it into the industry and change things there. With regard to the pipeline capacity, clearly not, in many ways, not a desirable development for our regions. I mean, if we want to build up an industry and value in our regions, we need to make sure that these resources need to be converted here and we don't just ship it out of the region. But again, I mean, I talked sort of a little bit tongue-in-cheek about the Silicon Valley between Pittsburgh and Morgantown for a new natural gas industry. I mean, we have the natural gas industry or the petrochemical industry Silicon Valley in Texas, right? I mean, all the expertise is there, the plants are there, everything is there. So there is a large driving force to say, hey, let's just build the pipeline and continue doing down there what we're doing. It's difficult to go up against that. And again, we won't be able to, in my opinion, we will not be able to go up against that by building a mirror image of the industry down there, now here in the area. We need to build something new, something that looks different, that is attractive to bring in new people, new players, and really build it sort of from the ground up. And I see an opportunity in these intensified processes.
Yeah, I sometimes thankfully don't work with undergrads. Though I do appreciate their energy. But certainly when we talk about how we educate and what we're looking at, we do a lot of talking about distributed generation and opportunities in our energy and sustainable development curriculum and what the opportunities are to evolve. And some of these technologies really can be disruptive technologies, and I mean that in a good way, of really changing how we think about and how we do things. From the pipeline perspective, right now, it depends on how much gas we're talking about taking away. I mean, if you look at some of the numbers for the region, we can support an awful lot of manufacturing in the region and still ship a lot of gas away. And both resources would be having value. That is, it can go and provide natural gas to other parts of the country as well as support industry here. I think one of the places on a regulatory side is we can look at is how do we better support long-term purchases. And as you get plants coming in and saying, you know, if $1 an MCF is an acceptable price of coming in and having some long-term gas purchase agreements to do that and figuring out how to facilitate that so that they can ensure they have the feedstock that they need to build and maintain a plant. I mean, that's really the risk. You build a $6 billion plant. If your natural gas is at $12 an MCF, that plant's not going to operate. And so being able to lock that in. So I think it's a concern, but I think it's overstated right now, at least based on the supply that I see available in the 5 to 10 year horizon, or even 5 to 20 year horizon when you think about what some of these plants would need. I think we can do both.
This question would be for Josh. You talked about transportation and using a different kind of a fuel. I'm wondering if you would offer some more comments on what you see happening in the future. Would natural gas be so inexpensive we can move to electricity? Would it supplant the usual gasoline? You remember we talked about hydrogen as the fuel of the future,
Sure.
And the joke is it always will be. And I don't know what you would say about transportation now.
I think that's right. I mean, one of the things is I look at markets and how things have evolved through subsidies for things like hydrogen vehicles, and we can do it, but we can't do it at scale, right? You can lease a car for inexpensively, but the Honda Clarity still costs you about, if you were going to buy it as a $300,000 or $400,000 vehicle at least, right? Nobody's going to buy that vehicle, and so. We're seeing things like Tesla and the Chevy Volt and the Nissan Leaf and some other, they're small-scale innovations, but they are at market. And if you look at where Tesla is, particularly with the sales, and we'll see if their Model 3 can actually come online and do what they've hoped to do with it. But that's where I think we're going to be able to generate electricity relatively inexpensively, or at least stably, for the foreseeable future, which suggests that to the extent oil products, gasoline particularly for transportation, that price is going to be more volatile and is going to go back up at some point. At least there's nothing to suggest that it won't. When is a bigger question. I think that we will see those prices go back up. At least that's what I'm seeing, which will make electricity more and more viable as we see. You know, now some of the Teslas can be charged to 80% power in less than 20 minutes in the right spots. That starts to look like an oasis stop. If you're going to stop at the Burger King, if there's a place to stop it. I don't like Burger King either, but that's whatever's at the oasis is what you're stuck with. That this, in fact, does become a viable technology. And that's where I think that if you're going to fuel switch, you do to one that already is starting to get a foothold on the market. And that's why I say natural gas can be part of the transportation sector, but I see it as via electricity most likely. And it makes some sense. People are not readily making changes from, you know, technology to technology on that front, and so one fuel switch is asking a lot. And so my sense, and you know, hydrogen isn't a fuel really, right? I mean, hydrogen really is the storage capacity. You use electricity, so if it's coal-fired electricity to make hydrogen, it's coal, and if it's wind, it's wind, and if it's water, it's water. And so I don't see, it seems to me that you would do other things with the hydrogen as well, because then you have to build a new infrastructure, whereas electricity infrastructure, while it would need to be upgraded for all of us to run on electricity, as we get a smarter and smarter grid, it can be a resource that the cars can be a resource for storage as well. So
That's great. I think we're just about on the schedule to complete this, and before we go to the next door for reception, let's thanks to the two speakers.